Hello everybody, this video is going to be about something called ICE tables. Sometimes you may hear it called a rice table as well. This is going to be a technique that we use to organize our data and our thoughts for equilibrium type problems. So a lot of times we want to know what the concentrations are at equilibrium. And so we're going to need our law of mass action, our equilibrium expression. We'll need our K value, and then we plug things in and we solve for what we're interested in. The problem is that there's a lot of numbers to keep track of, and things are changing, but we don't know by how much. We have some variables thrown in there. So we really need to be able to organize ourselves. And so if we want to be able to determine the concentrations of things at equilibrium, we're going to use the ICE table method. Some teachers are going to call it a rice table, but ICE table tends to be more common. So what is an ICE table? It's just us organizing things into a chart. That's all it is. We have a chemical reaction. ICE is going to stand for initial, change, and equilibrium. We literally set up a chart like this. You're going to have the chemical reaction at the top. You're going to have a column for each of the chemicals that are involved. You have a row for I, initial, C, the change, E, equilibrium. I personally like to throw in these last two, okay? I like making a row that says 5%, and I like a row that has the actual final answer in it. A lot of teachers don't put these last two rows, they just do the first three. So you can see it's called an ICE table because of those abbreviations we use. And because we always write the reaction at the top, sometimes people call it the rice table, okay? We're going to walk through this piece by piece. I'll kind of show you what we plug in where, what I mean by 5%. We'll go through all of that. Please, please, please glue in the steps that are a glue in for your notebook. Do the practice problems with me. Make sure you're writing little notes and annotating and little comments to yourself so you remember what we were doing. Make sure you're really thinking about this as we go. ICE tables are a really important skill because they can be useful for so many things. In AP Chem, I swear everything turns into an ICE table. I mean, not really, not for real, but they do show up in a lot of places. Being able to put your data into a chart to help express what's happening is a very good skill to have. All right, let's do our first practice problem. We're actually going to start with one of the harder ones. We're going to do like the worst one first, and then I'll show you a trick that makes them a lot easier. So, you have an initial concentration of 1.3 molar. What are the concentrations of the products at equilibrium? Assume all reactants and products are aqueous and that your K value is 78.3. And there's your expression, or there's your reaction right there. So, what we're going to do, we're going to set up our table. Take a moment, right? We should have our equation at the top. We should have a row for everything. If you're using lined paper, graph paper, and you're very neat and tidy, you don't necessarily have to draw lines between them. If it helps keep your information cleaner, more readable, then yes, put the lines. Okay. Now what we're going to do is we're going to fill in the row for the initial concentrations. They told us that when we start, our concentration of PCl5 is 1.3. So I'm going to put a 1.3 here. Now when I start this reaction, I don't have any products yet, do I? As of right now, I don't start with anything, product-wise. I only have my reactants. Next, what we're going to do is we're going to think about how things are going to change. You have to make sure that we take into account our coefficients, okay? We don't know by how much this decreases. We don't know by how much this increases or this. We're going to need to use a variable because it's an unknown amount. I don't know how much change is going to occur. I know there's going to be a change, but I don't know what number. So what I'm going to do is I'm going to say, well, let's think about this. My reactants are going to go down, so it'll be a negative change. My products are going to increase, so it's going to be a positive. This is a 1 to 1 to 1 ratio. So for every one of these that gets used up, one of these gets made and one of these gets made. So I'm going to have minus some amount, minus x, I don't know. I'm going to have a plus x and a plus x. You have to make sure that you take your coefficients into account in this change row. If I had had a 2 over here, then this would be 2x. If this had had a 3 over here, this would be minus 3x. So your coefficients are going to show up in this row. Make a note to yourself in your notebook right now. Don't forget your coefficients. That's a common mistake. Okay. Next, we're going to write out what the concentrations would be at equilibrium with the variable in place. So at equilibrium, I started with 1.3 and I lost this amount. So at equilibrium, my concentration is 1.3 minus x. At equilibrium, I started with a 0 and I've gained this amount. So my concentration is x. And over here, same thing, my concentration is x. Make sure you're careful with those plus and minus signs. Be very careful with those. Sometimes I like to joke that all chemistry is seeing if you can keep track of positives and negatives, because that's what it feels like some days. All right. Now, there is a trick that we can sometimes use called the 5% rule. In order to use the 5% rule, you have to meet some conditions. This problem does not meet these conditions, okay? So we are not going to be able to use the 5% rule because our K value is greater than 1. So this is just going to be not applicable this time. We do not get to use our shortcut. Because remember, right, it told us that our KEQ is 78.3, which is greater than 1. Can't use the shortcut. Another thing to think about is which direction is the reaction going. If I need to write an equilibrium expression to do this, do I write the equilibrium expression for the forward reaction, or do I write the equilibrium expression for the reverse reaction, the backwards reaction? In order to determine that, I have to look at my Q value. So the forward reaction is happening because I literally started with no products. I only had reactants, so I had to go forward. So that means I'm going to be writing the expression for the forward direction, which means my equilibrium expression, my law of mass action, ends up being that. Sometimes you will have a Q value that indicates you're going backwards. And if you don't bother to check, you're going to get everything wrong. So always check which direction is happening. Okay? Really, really important. All right. Next, what we're going to do is we're going to use this equilibrium expression. We're going to plug in our K value. We're going to plug in the concentrations that are happening at equilibrium. Remember, there's x's involved. And we're going to solve for x. So here's our chart. We're going to plug everything in that we know. You're going to use these values. The K value is equal to the concentrations at equilibrium. Not when you start, not the change. It's the ones at equilibrium. We had our K value given to us. Remember, it was 78.3. So I plug that in and I get 78.3 equals x times x over 1.3 minus x. Uh-oh. Some of you should notice that that's a pretty ugly problem to solve, isn't it? That's a lot of x's happening. That right there is going to require that we use a certain equation from our math class. Let's try to, simplify this a little bit. Let's try to get rid of that fraction, combine like terms, all that kind of stuff. Totally fine if you do it in a different order. This is what I do. And then I'm going to move everything to the same side. Now, that right there should jump out at you. That is in a very specific format, isn't it? That is in a format that requires us to use the quadratic formula. Yuck. Okay, so remember from math class, if you want to solve a quadratic equation, you got to use this crazy, horrible formula. Our equation is in this format, ax squared plus bx plus c. So I have to look here and say, okay, a would be a 1, b would be 78.3, and c would be negative 101.79. I have to plug those values into the horrible equation. Remember, you're going to get an answer where you do a plus here, and then you get a second answer where you get a minus. When you plug in these numbers to this equation, this is what it should look like. Negative b plus or minus the square root of b squared minus 4 times a times c. Divide that whole thing by 2 times the a value. Why don't you go ahead and try to get those actual numbers? You should get an answer when you did a plus here. Then you should do it again and get an answer when you get a minus. All right, if you solve that both times, you're going to find out that x has two possibilities. X can either be 1.28 or it can be negative 79.58. One of those answers makes sense and one of them is nonsense. One is not going to work based on the context of what we're doing. Remember that x was the amount of product that you made. It is the increase in molarity. Well, if I'm trying to make X amount, how can I have a negative? That makes no sense. It has to be this. Sometimes you're going to figure it out based on the positive or negative amount. Sometimes you're going to be having to look to see, like, you might end up losing more than you started with. Well, that's not an option, right? So you have to think about which one makes conceptual sense. So what this is telling me is that my x value, the change that I'm seeing happen, is 1.28. That's horrible, isn't it, having to do all this? The nice thing is 95% of the time our 5% trick is going to work and we don't have to do this most of the time. Yes, I know your graphing calculators can solve this for you, which is awesome. Realize when we're on campus sitting in your desk taking a quiz all by yourself, you use my class calculators, which are scientific, non-graphing calculators. You would have to be able to do this yourself, okay? So just something to keep in mind that you do not always have access to the internet or to a graphing calculator. All right, back to our chart. Now what we're going to do is we have to plug in our x value here to find out what the concentrations would be when we're finished. Sometimes people have a tendency to solve for x and they're so happy. They're like, I just did so much work. I just did that horrible quadratic equation. I have my x value. I'm all done. And they forget that they never actually answered the question. So you have to come back and find out what your concentrations were for everything at the end, which is why I like having a row added to my chart specifically for this, okay? So 1.3 minus x, which was 1.28, tells me that when I'm done, I just have a teeny tiny bit of PCl5 left. I only have 0.02 left. It increased by x. X was 1.28, so when I'm done, I have this much and I have this much. Okay. You're not always solving for the amounts at the end. Sometimes you may be solving for how much you started with. Sometimes you may be solving for what the change was. Sometimes you're given these and you're solving for K. Sometimes you might have numbers here instead of zeros, and that's just adding a little bit more complication to the math, but you would do everything the same way. So sometimes you might be given moles and you have to then calculate the concentration, right? So sometimes they can get a little bit more involved, but the format will always be the same. You're always kind of plugging things into a chart and using that law of mass action, that equilibrium expression. Now let's do a problem where we get to use the 5% rule. Okay, let's look at our trick since 95% of our time is spent using this trick. Because that equation's awful. There is a better way that for most of everything will work. The 5% rule. So some conditions that have to be met, all right, in order to use this rule to simplify our math. You can only use it when x is very small. If there's just a little bit of change happening compared to the concentrations that you start with, then we're just going to decide it's not enough to really matter, so we're going to just call it negligible, okay? The change ends up being so small that if we were to even take into account our sig figs, it would be within the range of potential error. And so who cares? Ignore it, okay? We're going to ignore the x part in certain places of our ICE table. And that will take away our need for the quadratic equation. So 5% rule is because x is going to have to be less than 5% of the concentrations you start with. So negligible, first you got to have k less than 1, okay? And x is going to be 5% or less of the initial concentrations. The problem is you can't know if x was small until you finished the quadratic equation, which is horrible, right? You're kind of in this like circular reasoning here. Like, how do I know if I can use it if I can't tell until the end of not using it? So what you're going to do is you're going to guesstimate. You're going to do a guess. If K is at least 1,000 times smaller than your initial concentration, you stand a good chance of the 5% rule working. If you're 900 times smaller, probably, maybe, I don't know, you gotta guess, right? You're guessing. So what you're gonna have to do at the end is check whether or not it worked. So once you use the 5% rule, you've simplified your math, you've avoided the quadratic equation, you gotta check to see if it was a good guesstimate. So X that you solve for over your initial concentration times 100 needs to be less than 5%. Okay? So if that's true, great. Proceed on to the next question. Your guesstimate was good. You are allowed to use the 5% rule. If you end up with a percent that's larger than 5%, you got to go back and redo the whole thing. You got to go back and redo the whole thing with the quadratic equation. But here's the thing. If that's only going to be true 1 out of 10 times, then you are going to still save time in the long run, assuming that you can use the 5% rule and checking at the end. Once in a while it won't work, you start over. But you gotta assume it's the 5% rule, assuming you meet those conditions you see on the screen. The nice thing is, even in AP Chemistry, almost always 5% rule works. Now, people will always say, like, well, why 5%? Why not 3%? Why not 10%? It's arbitrary. It's just a cutoff. People have all agreed 5% is going to be enough. That 5% will typically get you in the window where your sig figs are going to be, an issue, right? So 5% is good enough. All right, next problem. In the following reaction, your equilibrium constant is 9.3 times 10 to the minus 7 at room temperature. Calculate the equilibrium concentrations in your flask containing only 3 molar of NO2. So here's your equation. You need to set up your ice table using this equation. So why don't you pause and try to set it up? All right, let's look at what the ice table should look like. You should have the reaction at the top. You should have a column for each chemical. You should have a row for each ICE, your 5%, and your answer at the bottom, like that. Now it's time to plug in our information. It told us I started with 3 molar of this. I didn't start with any of this, it's just a 0. This is the row where we have the X's. But look, 2 NO2. That means every time this reaction goes forward, 2 of these are going to disappear. So it's not minus X, it's minus 2X. Over here, every time 2 of these gets used up, 1 of these gets made. So this is a plus X. At equilibrium, it'll be 3 minus 2X, and this will be X. Now let's see if we can use the 5% rule. Let's double check our conditions. Is K less than 1, and is it at least 1,000 times smaller than your initial concentrations? Is this at least 1,000 times smaller than 3? Yup. That means I can probably use the 5% rule. So what I'm going to do is I'm going to ignore any place where X is being added or subtracted from another number. So instead of saying 3 minus 2x, I'm assuming that this is so small I don't care. Compared to 3, this is a tiny amount. Just leave it as a 3. Here, you got to leave the x values that are by themselves, because while x is tiny, compared to 0, it still matters, doesn't it? Compared to 3, it doesn't matter. But when I'm comparing it to literally nothing being there ever, and now suddenly there is something, that is meaningful. So if x is by itself, you leave it there. What this does, what this accomplishes for you, is it gets rid of this yucky part, doesn't it? This part right here is what's requiring us to use the quadratic equation. So I'm just ignoring it, and I'm just going to leave it as a 3. Some people will say, could I use the quadratic equation every single time because it's more accurate? And my answer is no, because one of the things we're assessing you on is, do you understand and can you apply the 5% rule when it's applicable? So while yes, your answer may be technically more accurate, it doesn't mean you're doing it right. Doing it correctly is using the 5% rule, because that's how we do things in chemistry, okay? So just make sure you're not ignoring the 5% rule. Now what we're going to do with our chart is we're going to plug our 5% rule values into our equilibrium expression. So products over reactants, don't forget that this is squared because of our coefficient. You're going to plug in your K value, which we told you in the problem. Now we put an X on the top, divided by 3 squared. Isn't that way better? That is so much better. That is way, way better than having to do the quadratic equation. What I'd like you to do now is calculate your X value and then figure out what your final answers will be. Do not use the equilibrium row to get your answer. Use the 5% rule, or 5% row, to get your answer. Okay? So pause and try to fill out this very last row. There we go. X is 8.37 times 10 to the minus 6. That is a teeny, teeny, tiny amount different than 3. Remember, we're just going to let this stay 3. But compared to 0, this is enough to matter. Those are my final concentrations. Now, you're not done. When you use the 5% rule, what are you supposed to do when you're finished? You're supposed to check if it was valid or not. Use this, pause the video, and see if it was valid. Were you, after all, allowed to use that 5% rule or not? All right, well, our X value was 8.37 times 10 to the minus 6. I divide it by my starting concentration, which was 3. I'm going to multiply by 100, and we're going to see what we end up with. There we go. Yes, this was less than 5, so this was valid to use the 5% rule. One of the things that's nice about ICE tables is if you get really good at them, they make other chapters easier. You can even use these ICE tables in acid-base problems, because acid-base reactions can go both directions like equilibrium, so you could use those for acid-base. I've even seen people try to teach stoichiometry using these charts before. So you can actually apply this technique to lots of other chapters, and in AP chemistry, that's something they like to do. They like to see if you can apply this technique to more complicated problems. So it's really great if you can get good at your ICE tables. Okay? All right, everybody, that was it for this video. I hope that was helpful. Bye.